All right, so here we go with, suppose there are 6 times 10 to the 9th people on Earth, all of whom are in the state of Connecticut, so everybody gets a square meter to themselves, and each person has a 100 kilogram mass. Everybody jumps 1 meter into the air at the same time. The Earth itself has a mass of 6 times 10 to the 24 kilogram, and the width of a carbon atom is 10 to the negative 10 meters. A carbon atom width is called an angstrom. It's a special unit of length to measure things that are really, really small. All right, so when the people jump, the Earth and the people move, right? The Earth moves because Newton's third law. Object A exerts force on object B exerts force on object A in equal magnitude and opposite direction. But what doesn't move? Well, if you were paying attention, you know the system's center of mass. System's center of mass does not move. So we have the Earth, and then we have the people jumping, and the Earth is going to pull down on the people are going to pull up on the Earth. Meanwhile, the center of mass, even when you have the people standing flat on the Earth, not that the Earth is flat, but when they're standing on the Earth, the center of mass is going to be right there. Center of mass here, with all of these people, where is it going to be? Well, the center of mass for the system is not going to move, right? So that's kind of a spoiler here. How far will the Earth move when all of the people jump? So let's go back to our equation. The equation for a center of mass for a two-object system. It's the mass of the first object, in this case the Earth, times the change in position, which is what we're looking for. The initial position we can say is 0, and we're looking for that final position, equals the mass of the second object, the people, times their change in position, which in this case is 1 meter. So the mass of the people, each person weighs 100 kilograms, and there's this many people on Earth. So we're going to multiply 100 by this. Another way to write 100 is times 10 to the second. So we can just add the exponents here. Think about those exponent rules. They're going to come into play later too. Times 10 to the second, which gives us 6 times 10 to the 11th kilograms. Times our change in position was 1 meter. The mass of the Earth was given to us as 6 times 10 to the 24th kilograms. And we're looking for that change in position, so we're still going to call it out x. All right, solving for x, we get 6 times 10 to the 24th, 6 times 10 to the 24th, dividing it on each side. The 6 is going to cancel. We have 10 to the 11th in the numerator, 10 to the 24th. There's the exponent rule again. This time we're dividing. So when we're dividing, we're going to do 10 to the 11th minus 10 to the 24th times 1. So we get times 10 to the negative 13th meters. And if that makes you uncomfortable, you can put a 1 in front. It means the same thing. 1 times 10 to the negative 13th meter. Obviously, if an angstrom is the width of a carbon atom, 10 to the negative 10th meter, this is 1/100th of the width of a carbon atom. So its center of mass is still right there. Okay, for the next problem, I'm going to go through another version of this equation. It's basically the same thing. To find the center of mass for two separate objects, this is just an alternative way. Do it your way. I like this way, and I want to introduce it to you because I think it makes sense. So to find the center of mass for 2 or 4 or 10 or however many objects, you can just take the sum of an first object's mass times the position of that object's center of mass plus, well, that's what the sum of means. Silly. And divide that by the sum of all of the masses. So if you have two objects, then you would take first object times the center of mass of that first object, then add that to mass and so on. It's going to make sense when I show it to you. So here we go. So we have the first object. So to find the center of mass for this whole system, we're going to take the mass of the first object, which we'll call the cart, and the position of the center of mass here is going to be, if this is 6 long and it's exactly the same on both sides, then the center of mass is going to be right there. So 100 times 9 plus, second object is 50. And where's the center of mass there located? It's located at 6. Divided by the sum of both of those masses. So we get the 109 plus, so we get 900 plus 300, which is 400, doesn't even matter. 900 plus 300, which is 1200, divided by 150, which equals 8. So that means the position for the center of mass for both of these things, for the system's center of mass, is going to be at the 8-meter mark. Now we know that center of mass is not going to change. So we know the center of mass is still going to be right here. So what's going to happen as he walks? The cart's going to go backwards because the cart is going to push him forward, and therefore the cart's going to go backward. It's sitting on a cart with a medicine ball and pushing it forward, you're going to go backwards. It's the same situation. So we're going to end up with a mirror image of this diagram. Yeah, this is my cart. Deal with it. Center of mass is still going to be here. That's not a mirror image. They're just competitive. Center of mass is still going to be at 8. The cart is going to 1, 2, 3, 4. 1, 2, 3, 4. Right, so it's a mirror image. And then 1, 2, 1, 2. Person standing right there. Center of mass does not move. Boom. There you go. That's all I've got for center of mass for you at this time. I think this is a useful way to look at it. If it still confuses you, that's fine. That's fine. Use the first equation.